Greetings. My name is Elizabeth Wade. I teach basic calculus for the mathematics department at Pellissippi State Technical Community College. This is topic 3 on applications of derivatives and segment 3.2 on curve sketching. The derivative can tell us a great deal about the shape of the graph of a function. Notice that over this interval, this graph is increasing. If I select a point on the interval and draw a tangent line to the graph at that point, observe that this line has positive slope. Therefore, we have the rule that a function will be increasing on an interval if the derivative is positive for each value of x in the interval. If the slope is positive, the derivative is positive. The graph of this function is decreasing on the interval shown. If I select a point on this interval and draw a tangent, this tangent line has negative slope, so the derivative is negative. So we have the rule that a function will be decreasing on an interval if the derivative is negative for each value of x in the interval. We need to talk about the definition of critical values. Critical values are values of x in the domain of a function where the derivative is either equal to 0 or where the derivative does not exist. We can establish now a procedure for determining relative extrema and the intervals where a continuous function is increasing or decreasing. Extrema means maximum or minimum points. Consider the function f of x equal x to the third minus 3x squared minus 24x plus 32. Notice that the derivative of this function, by the rules that we've learned, you'd bring the 3 around, decrease the exponent, 3x squared, minus, swing the 2 around, 6x, minus 24, and the derivative of 32 is 0. So this is the derivative, and I want to determine the critical values of this function. So I'm going to take the derivative, 3x squared minus 6x minus 24, and set this equal to 0. And solve this algebraic equation, this quadratic equation. I'm going to try factoring it. So I'll factor out a 3 first. If factoring fails, remember you can use the quadratic formula. You could also graph this function and find its zeros. Continuing to factor, x plus 2, x minus 4. And so I get two critical values, one at an x value of negative 2 and one at an x value of 4. So this is where the derivative equals 0. Also, critical values can be obtained when the derivative does not exist. But since this is a polynomial, it's defined for all real number values. Let's identify now the open intervals that are determined by the critical values. So in our example, we have critical values at negative 2 and at 4. So that defines 3 intervals. We have the interval from negative infinity to negative 2. We have this interval which runs from negative 2 to 4. And then we have our third interval which goes from 4 to infinity. Now you have to select a test point in each interval and determine if the sign of the derivative is positive or negative. There are several ways to do this. One way is to just select a point, like on the interval from 4 to infinity, I might select 6. Plug 6 into the derivative and determine if it is positive or negative. I prefer to use the graph of the derivative to determine this instead of selecting test points. So here I've graphed the derivative, 3x squared minus 6x minus 24. This is negative 2. Notice that the derivative is equal to 0 at negative 2. And again, the derivative is equal to 0 at 4. Notice that to the left of negative 2, the derivative is positive because it's above the x-axis. And in between negative 2 and 4, the derivative is negative, and then it goes back to positive. So I'm going to identify this on my sign chart. The derivative is positive from negative infinity to negative 2. It's negative from negative 2 to 4. And then it's positive from 4 to infinity. So according to the rules that we just established, when the derivative is positive, which is the case from negative infinity to negative 2, the function is increasing. It's also increasing from 4 to infinity. And then from negative 2 to 4, the original function would be decreasing. In addition, the first derivative test states that as we move across a critical number from left to right, if the derivative changes sign from positive to negative, then f of c is a relative maximum. That is, the graph goes from increasing to decreasing. Let's look at our example. We had critical values at negative 2 and at 4. We showed that the derivative was positive on this interval, negative on this interval, and positive on this interval, so that the original function was increasing from negative infinity to negative 2, then it decreased from negative 2 to 4, and then it went back to increasing. So observe that at x equal negative 2, I would have a relative maximum according to this statement, because the function goes from increasing to decreasing. And then in a similar manner, you'll have a relative minimum if the graph goes from decreasing to increasing. That is, the derivative changes sign from negative to positive. So in our example, there should be a relative minimum at x equal 4. Let's switch to our virtual calculator and examine the graph of this function and see if this is true. First, we have to enter our function under y equal. So I've typed in x cubed minus 3x squared minus 24x plus 32. I chose for my window negative 10 to 10 with a scale of 1, and negative 75 to 75, and I used a scale of 75. Now let's graph our function. Remember, this is the original function. And notice that the graph achieves a relative maximum at negative 2, and it appears to achieve a relative minimum at x equal 4. Now let's go back to our notes. There's another point of interest on our graphs, and that's a point where the concavity changes. If the concavity of a graph changes, then that point is called an inflection point. In economics, this is often referred to as a point of diminishing returns. In order to find inflection points, we use the second derivative. So for our example, the first derivative was 3x squared minus 6x minus 24. So the second derivative would be, bring the 2 around, 6x minus 6. And remember, the graph of 24 is 0. So 6x minus 6 is the second derivative. Next, you would identify the open intervals determined by the c values for which the second derivative is 0 or the second derivative does not exist. Well, in our case, we have 6x minus 6, which is a linear function that would cut through the x-axis at x equal 1. This would be 1 on the x-axis. You can graph this if you want to. I know the graph has positive slope, so it would be headed in this, the line would be tilted this way. So it would be negative to the left of 1 and positive to the right of 1. You can also just select a number greater than 1 or a number smaller than 1 and plug those into the function to determine where it's positive and where it's negative. So the rule states that the original function will be concave up for values of x where the second derivative is positive, and it will be concave down for values of x where the second derivative is negative. So after we set 6x minus 6 equal to 0 and determine that that is at x equal 1, then we would observe that for values of x less than 1, the graph would be concave down, and for values of x greater than 1, the graph would be concave up, because the second derivative is positive. So at x equal 1, the concavity changes, and so there is an inflection point at x equal 1. Now let's switch back to our calculator and check all this. This is the graph of the original function. Notice that our function is increasing on the interval from negative infinity to 2, and then it's decreasing to negative 2, and then from negative 2 to 4, the graph is decreasing, and then from 4 to infinity, the graph increases. Notice also that we have a relative maximum at negative 2. If I wanted to determine the y value to go with this point, I could go to Trace, type in negative 2, and press Enter. So this point is negative 260, this relative maximum point. We also have a relative minimum at x equal 4, so while we're still in the trace mode, let's type 4 in, press Enter. So at 4, negative 48, we have a relative minimum. And then according to our work with the second derivative, the concavity of this curve changes from down, this curve is concave down here, to up at x equal 1. Let's see what the point is. 1, 6. So at 1, 6, the concavity is switching from concave down to concave up. And again, in the business world, in economics, this would be the point of diminishing returns. Well, that's it for this segment. Now you need to practice this concept by working similar problems. Thank you.